there's more to Spotify than meets the ear. That's because video is taking center stage on Spotify, with over 300,000 video shows and 300 million users already watching their favorite podcast. With seamless switching between watching and listening, you can tune in anytime, anywhere. Got a show of your own? Upload your video to Spotify, turn views into fans, and monetize your passion. I've been trying to
Good evening and welcome everybody. This is Obi-Wan Bez for in Simplex Pachinko. We are doing some math tonight, so we're back to our GRE schedule. We're working on cracking the GRE math test. This is the math subject test. Several people have asked. And right. Several people have asked, and yeah, it's the actual math exam. This one's the one that goes through basically everything you should know before you go into grad school in mathematics. So we're going to be slowly working our way through literally the entire book. Eventually we're going to get up into some of the higher stuff, which some of which I have never actually learned before, so we're going to try and work through it and see if I can make sense of it. So, from last time, just real quick, right? Last one we had was let x be a real number such that sine of x is 1/2 and x is between 2 and 3. What is the value of cosine of negative sine of x? Okay. We said that we got root 3 over 2, and I was ever so slightly unsatisfied with the answer, if only because I think it was what I plugged in my calculator did not come back with a sensible answer. Now it could be that the settings are messed up, and you do want to check. That should be like the first thing you check, is to see if you have made a mistake. And that is a practice. Yeah, that's a practice exam all the way at the end. Okay, practice test solutions. Chapter review questions. There we go. Right, so we want the chapter 1 review. Hope everybody's doing alright tonight. Chapter 3. Chapter 2. This is chapter 1, number 21. Yep. Okay. So the way that they set it up was that we wanted to start with cosine of theta is equal to square root of 1 minus sine squared of theta, which is then, we had the sine, which was 1/2, and then that just got us 1 minus 1/2 squared underneath the square root, which does get us root 3 over 2 eventually. Yeah, I just did it as a picture. Basically, if you know your negative angle theorem, where like if you just switch the sign, switch the sign of the inside of either a sine or a cosine, we rely on its even or odd symmetry, right? Its parity, in order to determine whether this is going to have the same sign or opposite sign or neither. So in this case, it ended up with our cosine of negative sine of x is going to be the same as the cosine of the positive sine of x. It is an even function. Okay. Number 22. Reset the canvas. Which one of the following is in the domain of f of x equals log of sine of x? A is 11, B is 111, C is 1111, and D is 11,111, and E is none. Okay, so absolute quick and dirty way to do this, plug them in. So first off, make sure that your calculator is in radian mode. It is in degree mode. Hey, that would have fixed everything last time. Anyway, okay. So which of the following is in the domain of f of x is equal to log of sine of x? So if we want to do that, we just say, okay, assign y1 to be the log, which again, in this case, is natural log. It doesn't really matter, though, right? What is the point of all of this? Really, we want to know when is sine of x going to be greater than 0? Allegedly, that will only happen once. So we've got 4 possible answers to check, and it should only happen one time. So the log of the sine of x. If we then plug this in, now on a TI calculator, there are multiple ways to do this. It is the only calculator that I have significant expertise in, so sorry. But hey, it was designed that way. Oh, corporations. So if we go to, there's a button over here called vars, which stands for variables. So if you hit that one, we end up getting this long list. If you go over to yvars, and we are in function mode, so you hit function, and then y1. When you hit that, and then put a set of parentheses around it, you can treat it like function notation. So y1 of 11, error, non-real answer. So because we get non-real answers, we're going to assume here that, yeah, 11 is not going to be possible. If we do y of 111, we also get an error. Y of 1111 is also an error. 11,111 does have an answer. So these all have a sine of x which is going to get us less than 0. You can always go through and plug those in individually one at a time just to check. But D is going to be the answer for that one. Okay. Okay, so I don't know if you're going to be able to see this, but this is what we get when we zoom out. Yeah, we get some blue dots in there. Those individually are little tiny scallops, which go like that, which show us that there are a number of places where we do get active, valid answers for all of this. But not really everywhere. Looks kind of like this when I zoom in a bit. So I am at basically from like 100 to 400 or something like that on the scale in the x direction. So yeah, you can see that there are some areas where this function is going to be continuous, and there are some areas where this function is not going to be continuous. Pretty obvious, right? When we plug in sine values, right, our valid sine values are going to be where we have x belonging to anywhere from 0 to pi, not including 0 and pi themselves because that's where it's 0, and I guess technically, right, we're gonna have to move it that way. Right, from 0 to pi, with the caveat that we can move this around another rotation. So 0 plus 2 pi n and pi plus 2 pi n. They have to be the same number, of course. Right, so using this, how could we do this by hand, right? If we didn't have a calculator to just automatically plug everything in and then tell us what the answer is, we have to go through and say, okay, is 11 going to be between any of these? So if we go from, all right. Right, if we do interval, n is equal to 0, then we're just going from 0 to pi. Right, so obviously, we don't care about that one. That doesn't involve 11 at all. It's not even close. So this goes from 0 to 3. And change. Hey, Femvox, how you doing? Yeah, it's too bad for you, Leah, because I already have the best viewers. Bam! You are getting reported for spam. I mean, there's so many different options that we could put on here. 2150 British summertime. I guess right, 2050 UTC. Doing okay, yeah, nice. Many things, as always. Unfortunately, that may be a hijacked account. So if somebody hasn't been on in a long time, scammers tend to target those kinds of people, or at least those kinds of accounts. Nobody's going to notice if they get hijacked. Quietly take it over. Like a parasite. Alright, anyway. We know that 2 pi is approximately 6.28. So if we go to 1 or 2, right, then this should be going from 2 pi to 3 pi. And if we go to 2, this is going to be 4 pi to 5 pi. So that's what we've got for 11, right? We're going to go always from an even number to the next odd number of pi's. Sorry, even number of pi's to the next odd number of pi's. So in here, we're going from approximately, like I said, this is going to be like 6.28, and this is going to be 9 point something. So obviously that doesn't involve 11. And then here 4 pi is going to be 12 plus more, right? And then 5 pi is going to be 15 and more. Maybe even 16, right? So obviously, again, that doesn't include 11, so 11's out. Now, would I want to do this for all of them? It's going to take up a lot of time. But for what we're doing, we could also look at this and say, okay, what is the nearest even pi that we're going to get from each of these numbers? So if we go with 111, right, 111 divided by parentheses 2 pi, it's going to get us 17.666. Right, so that means that 111 divided by 2 pi is going to get us 17 plus this little bit. So one of the things that we could do is say, okay, well, 111 is going to then be equivalent to 17 by 2 pi plus this bit by 2 pi, 0.66619, etc., times 2 pi. Then we've got to figure out where's that. So if we subtract 17 from that number and multiply by 2 pi again, we get 4.185. So this part here is 4.185 radians. Where is 4.185 radians? Right, this is greater than pi. Or we could flip that around. Pi is less than 4.185, etc., which is also less than 2 pi. So this is in the underside so the sine of this particular angle, 4.185, etc., must be less than 0. So now we get a failure again. Right, so then again, we can do this as, so 1,111, let's see, divided by parentheses 2 pi, anyway, 176.8211. Now I can tell you immediately, 0.8211, it refers to the number of rotations that we have in excess. So, 80s children will know that one. So 0.82 rotations puts us back around underneath the unit circle. Yeah, that way. Puts us back around underneath the unit circle in the fourth quadrant. So that's also going to put us right over 2 pi is equal to 176.8211. And again, this tells us we're in the fourth quadrant because we are 82% the way around a rotation. So then we do 5 ones over 2 pi, and that's going to be right 1768.3705, etc. And now this is telling us we're in 37% of one rotation, so this is going to be quadrant 2. So we've just highlighted like 3 different ways you could go about this, maybe even 4, right? You could graph this thing and then find each of these locations and then figure out which ones have valid locations. So if you go onto the calculator, another way to do that is like zoom out until you get going from, let's say, 0 to 20,000. No, that's not what I wanted. Boo. All right, count by thousands. X's and Y's, I don't care, right? It's going to be pretty much just teeny. If we want to like argue about it a little bit in our heads, all of these values of sine of x are going to be, first of all, they have to be positive, and second of all, they have to be between 0 and 1. When it's between 0 and 1, the log of that is going to be a negative, yes, a negative number. So we're going to get something that's fairly small and negative, probably. So like we could go negative 5 to 0.5 or something like that, just to see how it looks. Right, and we get the same thing like I showed before. We got some individual tiny dots like way down here, which are usually due to like small areas of our domain that are actually included, but they're just like, at this resolution, they're essentially a single point. If we zoomed in on any one of them, it would get us a little bit of a curve, just like some of these other ones were, right? It'd just go like that and then be gone. Right, so in this window going from 0 to 20,000, I could then also go second calc over to value, and this is doing the same thing that the thing was on the home screen, where you just plug in a number, right? If I plug in 11, it'll pop up with x equals at the bottom. If I hit 11, then it ends up giving me a blank y value over here, which tells me that there is no y value. So it doesn't exist. If we go, and here's the other thing, if you just type the next number, it'll enter the next number. You don't have to go back in and, find retype everything or whatever. You just type the next number. So 111, again, give us a blank y. 4 ones gets us a blank y. And 5 ones now gets us the same negative 0.31956. And it shows us where that is in the grand scheme of things. Roughly about halfway through. Imagine that. Right, so that's how that works. We could, again, do this all on the home screen with actually, like, plugging in the numbers. And again, this was due, like, y1 of, with parentheses, in function notation. Works great, but it throws an error every time you do it, which can take up time. Instead of retyping everything, you can also hit second enter, which then allows you to get the previous, and then second enter the previous again, second enter the previous again, entries that you have put in. or the more modern ones, IETI 84-ish, 83 plus maybe, but 84 is like the standard these days. Or at least the standard if you're not going into engineering or math or science or whatever. And even then, it's pretty good. Hashtag not sponsored. It's just the one that I know how to use. And usually they allow you stuff like this in the GRE. So, yeah, you'd have to manually type it in or hit second enter a bunch of times. Or, like I said, the newer ones, if you just hit the up button, it'll go to the previous lines, and then you can hit enter and it'll retype it underneath. So what we've got here again was the one that worked was 11,111. Okay. 23. Right. Simplify the following. There was also a hint on number 22, which was you may use the fact that 1111 is just slightly greater than 353.64 times pi. So in that case, you can kind of break things up a little bit and say like, oh, well, if this number has this value, then if this number has this value, then the other numbers will be related by the following. I don't think that any of these are nicely divisible. I know that 11 will divide nicely into 1111, but I don't think that, let me see. Yeah, no. 11,111 is 100.099 times 111. And it is, yeah, 1,010.0909 times 11. So they're all just slightly off of multiples of 11, except 1,111 will be divisible by 11. Weird divisibility rule. No calculators at all. Okay. Oh, well. They may have an internal calculator, or if not, eh. Okay, well that certainly changes things a little bit. Really, that doesn't change my response to the last one, I suppose, is that what you'd probably be trying to do is take each of these numbers and divide it by, 6.28 or something really close to 2 pi in order to make sure that you figure out where on the rotation we are. So it's not necessarily the unit circle, just how far through this are we? All right, simplify. sure we actually circled the correct answer. Alright, so for the arc sine of 1/3, we end up with a triangle that looks like this. Not that one. It's that one. And when we have the same angle that's stacked on top, there are a few different ways to do this. One is to remember what the tangent double angle formula is. Honestly, I don't. We could derive it all the way over again if we needed to. Sure, why not? Right, so the tangent of 2 theta is going to be equal to the sine of 2 theta over the cosine of 2 theta. We already have the sine, so it'd be really nice if we could get everything in terms of sine as much as possible. We also need to know what the third side is, so that's going to be square root of 8. So that's 2 root 2. Up here, this is going to be 2 sine theta cosine theta. And down bottom is going to be 1 minus 2 sine squared theta. Right, this is going to be 2 times the sine of theta was 1/3, right, given. The cosine of theta is 2 root 2 over 3 over 1 minus 2 sine squared is going to be 1/3 squared. So we get 4 root 2 divided by 9, all divided by 1 minus, this is 1/9, so multiplied by 2 is 2/9. It's going to be 7/9 on the bottom, and then that's going to eliminate the 9s entirely. There's something there with a 7. Yes. That should be our indicator that that's the answer. Right, 4 root 2 over 7. Yep. All right. I find that probably the easiest way to figure all that out. Again, we're just trying to figure out what the tangent double angle formula is. If you know it, great. If you don't worry about it. You can always derive it from all these other bits. Okay, 23. 24. Last page, last 2 problems. Woo! Okay, simplify. square root of cosecant squared of arc cotangent of pi over 4 minus 1. Okay, so an arc cotangent is going to say, for what angle do we get this number? So pi over 4 is not going to be a nice number to get for an arc cotangent, or for a cotangent. So the problem is, right, this is saying cotangent of theta equals pi over 4. The trap, right? The trap is that we say, oh, the cotangent of pi over 4 is equal to 1. Ta-da! So the cotangent of pi over 4 is 1, and then the cosecant squared of 1, I don't know what you'd be thinking at this point, maybe even the minus 1 that's there, you're like, oh, that's inside the parentheses, right? I think you'd have to, like, compound the errors at this point. Yeah, there's not really a nice... it's not really a nice answer for this, even. To be like, oh, here's the obvious trap that they want you to fall into. Because again, you'd have to compound your errors and be like, the cosecant of 1 is going to be, and then have kind of a moment because you're like, wait, cosecant of 1 isn't like a nice number. You might, again, think of it backwards, that now we're doing the cosecant inverse. And how do we get a cosecant to be 1? That's going to be a pi over 2, and then we're going to square it, I guess. There is a pi squared on 16, so maybe that's like what somebody might be thinking about, but hey, thank you. On-screen calculator. Yep, okay. Oh, not available for subject. All right, that's fair. Unless approved as an accommodation. Okay. Yeah, the quantitative reasoning in general. I feel like there was something similar for praxis. Anyway, wouldn't surprise me. Negative 1, 1, pi squared on 16, pi over 4, and root pi over 2. Hang on. It's like the arc cotangent of 1 is equal to pi over 4. Did they fall into their own trap? It'd be really funny, but somehow I don't think so. Okay, no, actually, this is easy enough. Okay, so what we're doing is we're saying, what's the angle that's going to get us a right triangle again? This is going to be a cotangent that's equal to pi over 4. So a cotangent is adjacent over opposite. So adjacent is pi, opposite is 4. Right? So then we have to take the cosecant of that angle. So cosecant is the sine, multiplicative inverse of the sine. So we do need to figure out what the hypotenuse is going to be. So square root of pi squared plus 4 squared, 16, right? And then the cosecant of that is going to be equal to that stuff over 4. Pi squared plus 16 all over 4. We need the cosecant squared, which is going to be pi squared plus 16 on 16. Right? And then minus 1. So cosecant squared theta is going to be equal to pi squared plus 0 over 16. So, no, that was the right answer. I don't even know what we're... I don't even know what's supposed to be objectionable in this case. So yeah, somebody's screwing it up a lot, such that my random brain connections just decided that was a reasonable, appropriate, wrong answer. May find that they got that question right. I can't even. All right, 25. Determine the exact value for the sum, right? Arctan 1 plus arctan 2 plus arctan 3. Okay, right, let's get the distractors in here. Guess they're not all distractors. Pi over 2. Pi. 3 pi over 2. Pi over 4 minus 1. And pi over 2 minus 1. Okay, so things to keep in mind, right? Tangent values are the slopes of the... Why, hello, Don. Hey, everybody, it's Don Factorial. If you're not already following Don, please do so. Don is one of our mathy friends who has done, well, let's see. We were playing Good Job with him a while back with the community. We unfortunately have not finished that game. We also did Red Dragon Inn, I think, and my stuff didn't work for that, but whatever, it's fine. I was selecting cards at random. Let's see. And in addition to other math stuff done, oh, you weren't. Good job. Okay. Residues, nice. Yep, Don has been doing complex analysis, as well as general relativity, and a few other just really cool and awesome things. So, in addition to gaming, typically plays DayZ, but also has some other interests as well. So, if you are at all interested, please give a follow. Don's awesome. And if you ever look at Don's tags, right, he's got, what was it? Ed Sheeran lookalike. So I decided to steal that from you, Don, sorry. And I put best candy dispenser lookalike. Yep, that's the entire reason I created this username in 2016. No, I created the username in 2016, but I was looking for a new username that was going to be more fun, I think, because like, you know, going with my previous one, which was like my name, was just really not going to work for me. I was like, nah. So I decided to go with that because I had the Pez dispenser sitting around somewhere, and I was like, that's it. Nobody else has this, I bet. I was trying to start a username on Project Alpha for Geek and Sundry. That's what it was. 2016. And I was like, I don't want my username to be stolen yet again. I mean, stolen. Somebody getting there first. Scooped. I don't want my username getting scooped yet again. So I decided to just abandon the old name interest trope that I was going with, which worked for, you know, like 10 years before anybody actually tried to scoop it. But yeah, I have a really common name, so in multiple respects. Okay, so tangent values are the slopes of the terminal sides. So this gives us a picture of 1, 2, 3, give or take. Ooh. We'll give these back. Perfect. Nobody will ever know. Right, and then we drop altitude down like that. Okay. So this is what we're working with. We need to figure out what angle 1 plus angle 2 plus angle 3 is going to be. Which, like, pretty inconvenient. Not gonna lie. Yeah, and like, you could do this one by elimination. Again, as Fembox was saying, there are no calculators allowed during the GRE, so like, you're not going to just be able to plug stuff in. Oh well. pi on 4 is less than 1, so minus 1 is going to be negative. So, yeah, that's not going to work. Arctan of 1 and 2 and 3 individually are less than... I mean, clearly we can just say that this is going to be less than 90 degrees. So 3 pi on 2 is 3 90-degree angles. So that's not going to work. You're absolutely right there. And in order to be less than, let's see, arctan of 3, actually, arctan of 2, right? Arctan of, nope, never mind. It's a sine of 2. No, sine of 1/2. Wow. Having a sine value of 1/2, get us that. Right, if we just assumed if we just assume that we're going to focus on the big one, right? This is going to be 3 over 1, which will get us a hypotenuse of root 10. Okay, so where does that put us? That is steeper than, right, a 60-degree angle will be 1 root 3, 2, right? This is our 30, 60, 90. Which means that this is taller than that. Therefore, it must be more than 60 degrees. In addition, 2, 1, right? Root 3 is approximately, what, 1.86 or something like that? Or 1.76? Been a while. Right, somewhere around 1.76. So the 2 is also going to be taller than that. Right, this is going to be square root of 5. Which means we have 2 angles which are now greater than 60 degrees. So I mean, it can't be root pi over 2 minus 1, because that's going to be like 0.5, right? And we're we're already over 2 pi on 3. All right, so the only one left is going to be pi. And arctan of 1 is going to be 45 degrees, or pi over 4, just by itself. I mean, it's got to be pi. So, arctan 1 plus arctan 2 plus arctan 3 is equal to 3.14159265.4. Bingo. I'm slightly hesitant about that, but yeah, that's has to be the case. So really the crux in that, figuring out that logic piece was, I think, here. You're looking at these two things must be greater than our 60-degree angle tangents here. So therefore our angles must be greater than two must be greater than two 60-degree angles. Strictly greater than two 60-degree angles gets us 2 pi on 3, and arctan of 1 is pi on 4. So therefore, adding those three up, we have to get pi, because again, it can't be 3 pi on 2. That's 3 right angles. It's smaller than that. And then pi on 2 is too small. And the rest of these are much smaller. So yeah, there's got to be a way to do it algebraically. I'll think about it. And we're going to take a break here for ads. We've got 3 minutes, and then we'll come back, probably do some workout, and then line up whichever workout you want there, guys, if you have the channel points to spare. And then we'll be back. All right, thanks everybody for coming, and see you in 3.
Let your music taste shine with Premium. Host a jam with your friends and share your favorite songs with the entire squad without ad breaks. You can also play your favorite albums in any order with unlimited skips and repeats. Tap the banner to learn more.
There's more to Spotify taking center stage on Spotify, with over 300,000 video shows and 300 million users already watching their favorite podcast. With seamless switching between watching and listening, you can tune in anytime, anywhere. Got a show of your own? Upload your video to Spotify, turn views into fans, and monetize your passion.
Alright, Don, you got it, the most punishing of them all. It's not technically true, I guess, but I don't like doing push-ups. Alright, now let's actually get you the other camera so you can see how much I'm cheating. Good idea to warm up first. Because otherwise it's gonna not be pleasant. Alright. Yeah, that's enough procrastination. We're gonna have to take this off and just put it over here, because, quite frankly, it's not gonna work if it's on my head. It keeps trying to slide off. Alright. And 1, 2, 3, 4, 5, 6, 7, oi, 8, 9, 10, 11, 12, 13, 14, 15. Getting old is the problem. 16, 17, 18, 19, and 20. Oi. And we'll throw another one in there. Mostly. Okay, so these are eskrima sticks. I'm learning eskrima, which is also known as arnis, which is a Filipino martial art that uses machetes. It was not quite approved for everybody to use machetes, particularly during Spanish colonization, so they switched to sticks in order to try and mask the fact that they're learning all sorts of cool defensive maneuvers And eventually the Filipino people rose up against both the Spanish and against the organized crime that was riddling the nation, and eventually Eskrima became more of a calm sort of martial art. Is that Phobos? Yeah. How's it going? Good evening. Think you know which one could do the most squats? Oh, that'd be an interesting one. I could actually do a fair number of squats in the, as far as I can tell, appropriate appropriate form. You know, the going all the way down and back up. Gotta do them like Cloud, right? So with Eskrima, there are a number of things that you can do. One is we can start with a single stick, and generally speaking, you're trying to protect your heart, your sternum area, and then using your machete in order to stave off attacks from somebody who is trying to come at you. Generally speaking, you're kind of like almost straight on. But then if somebody were to try to attack you, typically step out of the way, slash, do whatever you need to in order to extricate yourself from the situation. So the most basic ones are forehand strikes, which you use your offhand to balance, like counterbalance yourself. There are also overhead strikes, which come up and over and then get the person that way. Actually, I don't even need to do anything there. Typically, you're doing an overhead and then a single strike as well. Most of our like kind of standard strikes tend to go 45 degrees down. So you can create kind of a nice little area where you're just like, don't come here. We also have open stance strikes, which are out from here. And typically you're trying to run your forearm into your hand such that the stick actually whips further than just here. So it increases the speed of the tip, and it also confers a little bit extra force into it. There's also returning back to standard or the closed stance. So we come through this way, hit here, but instead of just going sideways, we also kind of go down a little bit, and that can flip this to go back up and over, and then we're back in closed stance. My instructor also tends to grab his just above his elbow here and like keep this as the resting position. If what he told me is true and you're trying to protect your sternum, this seems like a bad idea. But like, he's the instructor, so maybe I'll listen. We've also done a number of other movements that tend to go up to block. So this is I'm going to forget the name of it, but Categorization maneuver, I think, is the strike that comes down. Basically, you take the stance here and you sink your weight while you twist your body, and like this becomes effectively a whip where it will come around and down across your target. So that's another, again, 45-degree strike that way. Oftentimes, unless somebody has been trained in Eskrima or trained to fight against Eskrima, then they're not going to know where all these things are coming from. So if you have a club weapon or a literal machete and you are trying to defend yourself, like a lot of these maneuvers are absolutely devastating. Which is also true for like any martial art. But then we move to two sticks, where if some people were walking along in the Philippines and they would have like their stuff for the day on their machetes, and sometimes it was just as a sheath, sometimes it was like to look like a pole. And the thing was that like if somebody were to attack them, they could fairly easily draw them out of the stuff they were carrying or drop the stuff they were carrying and then be able to stand ready. So typically there were a few different ways to go from here. We've got standard both down strikes and up strikes. Again, approximately 45-degree angles. We have twin strikes. So these can come off the shoulders and go down. And they make a lemniscate shape, figure 8. My left wrist does not like doing these. So I tend to open up a little bit extra, which is bad, but I'm 40-something and... Okay, we also have the up strikes, so these can come off the shoulders and then up, and twin strike. You'd want to practice both with your right arm on top and on bottom, so you're not too dominant in one or the other. I wonder if anybody heard that. All right, and then so from here, typically you'd end up with a like some way in which you'd want to sink back into a ready position. I don't have a good way to do it, really. Maybe something like that, where we're coming off the shoulders, we're doing a twin strike, and then trying to follow. So in this case, we're not actually crossing the middle. The sticks are essentially running one right after the other, so arms get crossed and then arms uncross. So when they cross the middle, it kind of goes 1, 2, 1, 2, 1, 2, 1, 2, whereas in the other one they were going 1, 2 together. And there's also another one that goes... Well, I mean, they're crossing together, right? So they both cross each other in the middle and then cross each other again. So from here, there is the sticks to heaven, which we strike 45, bounce, or deflect, or we just manually deflect it with our arm. This is an upward strike, so we're going from sticks to heaven. So it's like an earth to air strike. And then we swap positions, and then it comes back down, and now we're on ready on the left. Do the same. And then we also do a heaven to heaven, where we do the same kind of thing, but instead of this one coming up, it comes across. So up here, it kind of makes it like a rainbow sort of shape. Going across, it connects with either the opponent's stick or the opponent right here, and then swap and back. But pretty much it looks the same. So there are ones that you can kind of... Nope. There are ones you can kind of combo and things like that. So there's all sorts of cool stuff. He was telling us this week, like, just basically try to be unpredictable and try out like different combinations of stuff. Oh, there's also a few others. One was the like Kadlik strike, but you're just coming from the shoulder up over the top, swiping across, and then doing the Kadlik here. So that's one possibility. And oftentimes you're using your body weight sinking down in order to drag this around faster. So again, it becomes more like a whip. And then there's also a 3 strike, which is a little weird, which we tend to go... oh, what was this one? Up. No, that can't be right. Yeah, here we go. So it's a standard 45-degree strike down, but then we bring the other one along with it. So 1, this one follows 2, and then this one comes up and over and returns as this goes to the shoulder. So 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. So it tends to go really quickly. And again, if you're trying to do like sticks to heaven, 1, 2, 3, follow, cross, follow, sticks to heaven, that was sloppy, and then 3, 3, Kadlik. Again, really sloppy, but I think that's probably good enough for tonight. Extended Eskrima edition. Woo! We just did 100 squats. Not tonight. Okay, so let's take a look at that fembox. Now their arms are all like jelly. We're gonna think about that one. Integral 1 over square root of square root of 2 minus cosine theta. 0 to 2 pi. Hey, Viv. Well, if it's a shift by a finite amount, then you just ask them to shift the hotel, right? You hold still, they shift the hotel. Should be easy enough. Alright, so Phobos, what I am going to see here is that right, since these are different things, we can think of this as d theta, yeah. Alright, we cannot think of this as an arctangent, because if it were an arctangent, then we would have to have a u substitution for the top. So that doesn't work. Right, our cosine of theta down at the bottom would be the u squared on top of that, right? This would just be u squared, and that's going to mess everything up. Oh wait, are you... This is complex, right? It's been kind of a long time. Residues? How about trigonometric integrals? Weierstrass substitution? Oh dear. Is that what you guys have been doing? Because I also don't remember that. It's been 20 years. Good news, the math doesn't change. Bad news, no clue. Yeah, there's literally a YouTube video which shows something almost identical. Yeah. So this one says if we let this has 2 plus the cosine of x dx in the denominator, or, you know, dx being up top, but in the denominator. So, yeah, I think this is probably going to be... Strauss substitution, let t equal tangent of x over 2, theta over 2. So arctan of t is going to be equal to theta over 2. Theta equals twice arctan of t. Yeah. I was looking at whatever website this is. LibreText. I always end up over there. Whenever I type anything in. It's just like, yeah, you probably want one of these. Can't remember if Grinfeld's book is also hosted there. Because I think he also has the Sigma. Or like his book is echoing their style or something. I don't remember what it is. Right, tangent, this is t over 1. This is going to be square root t squared plus 1. And then twice that angle. Twice that angle. That whole thing is theta. We want the cosine of theta as a whole. If this is twice as much, then the hang on, we looked at this just a minute ago. That'll be fine. Tangent of... Oh, no, because that's... 2 alpha. It's equal to... This was... I mean, we kind of want it the other way around. Alright, what is the... 2 tangent alpha over 1 minus tangent squared alpha. If we bump this over, this is 1 minus tangent squared alpha times tangent 2 alpha is 2 tangent alpha. This is tangent 2 alpha. Equals tangent 2 alpha plus, nope, times tangent squared alpha plus 2 tangent alpha. This is going to be gross. I know. Stop yelling. That's fun. Okay. Tangent alpha is equal to negative b plus or minus square root b squared minus 4ac, which is going to be plus 4, all over 2a, which is 1. Tangent alpha is equal to. This is going to multiply the denominator by 2 alpha. Going inside of the square root, we get tangent squared 2 alpha to multiply both of the terms on top, and a 2 is going to come out from each of those terms. Square root of this is just going to be a 1, and now plus tangent squared 2 alpha. Tangent alpha is equal to negative 1 plus or minus square root 1 plus tangent squared 2 alpha. 1 plus tangent squared is a secant squared. Not that I want to do that. Yeah, well, actually. I mean... cosine alpha plus or minus. This is the square root of the secant squared, which becomes a secant on the outside, and when we multiply everything by cosine, this is now 1. Simplifies nicely, at least. Alpha is now, oh wait, 2 alpha. Yeah, those are still 2 alpha. Do we just literally come back to the same? Well, not quite. Huh. That's actually slightly weird. Okay, so this is the tangent of theta over 2 is negative cosine 2, nope, 2 alpha is theta. Plus or minus 1 all over sine of theta. So that's weird, but okay. Next question, does that actually help us? I think we just spent a whole bunch of time that didn't really do anything. But that's fine. Technically, that's just t. Gross. Hey, bye, George. How's it going? Yeah, no worries. If anybody's interested, By George and I had a chat last night while I was doing Satisfactory, and she's... There we go. Pretty cool. It's like the worst introduction. Sorry, I haven't been over to your channel yet. That's the problem. But give her a watch, give her a follow. That's not what I wanted. That's not what I wanted to do. That one. Stream's been good. We've finished our, or no, we sort of finished. Cracking the GRE, it's Graduate Record Exam, for anybody who's taking a master's degree in mathematics or a related field. Typically has to take the mathematics subject test to make sure that their mathematics is up to snuff. So, we've been working on it a little bit for the past, this is night 11, so a few weeks anyway, basically a month. So anyway, yeah, it's been pretty cool. And we've been doing some problems that, like, we kind of get two different ways to do it. One is like the better theoretical algebraic method, which is kind of what you're seeing here on the screen. And then the quick and dirty, horrible, standardized testing way of doing things, which is, like, do you have the prerequisite knowledge to recognize that you don't have to do all of the work in order to solve the question, especially since they give you 5 potential answers. So it doesn't always work if you're just like, well, I just want to plug stuff in and see what happens. Yeah, a lot of these questions did not allow for that. Quick and dirty, yep. It ends up being kind of a lot of standardized testing in general, is like knowing how to play the exam rather than knowing the actual material, which is slightly sad. which is also why our country, the United States, is in such a problem. Because everybody's been worried about the exam, they don't actually teach the material. Yeah. So I was attempting, as I was making my exit from the United States a year ago, attempting to teach a better way of doing things. And so I picked up a... This is heavy into theory, so unless you're doing educational theory, and particularly mathematical educational theory, you probably don't want this book. But building thinking classrooms is basically like how to make students think again and try to actually work on like the in-class skills of how do we do things, not just, how do we get an answer. Yeah, it's that book is a lot of like how to take short-term mindset and start building it out. If anybody is interested, I just watched a pretty great video by Destin from Smarter Every Day. Now, granted, this is like a big... It was a month ago. It was
Is
kind
it
of
possible?
that one. The entire point was, can we actually make things in the United States anymore? Because, 99.9% of everything comes overseas. And he got into a discussion with a guy who was who developed a new object and tried to sell it online, but then they had to take the plans and ship the plans over to China, and then somebody over in China made a cheap ripoff, which basically undercut his sales almost entirely. And he's just like, but it's terrible. Like, the item that they're trying to sell is awful. Objectively, it's worse. And his was not that expensive, but it was still just okay. So Destin said, all right, that does it. We are going to make a grill scrubber out of chainmail, and it's going to have and they worked on a design that worked very nicely, and they were like, no, we can't send this overseas, because the second we do that, they're going to get cheap parts, they're going to undercut us, and then it's all over. So he made this thing. It is, I grant you, an hour-long commercial for their grill scrubber. However, it's also about the process of doing it and trying to get people to start thinking in terms of long-term investment, in terms of trying to get larger trying to get the industry back into a local mindset rather than trying to just, always ship everything out. Everything is in terms of short-term profit at the moment, right? So if you always concentrate on short-term profit, you're never going to end up doing the actual things that you want to do, and you're never going to end up making a good product. It's always going to be cheaper and worse. And it's always going to end up, it doesn't necessarily always have to be worse, but it's, it's going to trend that way, honestly. So this is yet another step in the awakening of Obi. So I am God, there's so much going on in my head right now. It's ridiculous. But yeah, it's just yet another link in the chain of how both sides here, both groups of people that are in our countries across the entire world, the people who are liberal or conservative, it doesn't matter. All of us need to work together to stop this nonsense, the short-term gratification, the focusing always on short-term profits. And like, again, both sides of the people want roughly the same stuff. It's just that there's a lot of propaganda coming down to keep us apart, because otherwise we would literally be unstoppable. I will say also, there is a company Demula's Market Basket in New Hampshire and Massachusetts is a good case study for, like, I mean, I'm just going to come out and say it, but like socialist policies with a lowercase s. In that Demula's basically did the thing that they did in the 50s, which was they gave people really good salaries, they gave people stock options in the company. Like, as they work over time, they accumulate stock options. And they got, like, people were being invested in a much larger sense than anything else. So it worked out really well. They used to pay anybody who was going off to college, like especially teenagers who were working there for years, would then decide, hey, I'm gonna go off to college, whatever. They would pay their like entire first year's tuition or books or like a certain amount of money essentially was the cap. Yeah. Demula's was great. It was always kind of like the crappy grocery store in my town. It was like always really dingy, and the lights were always sort of yellow, and like I hated going in there. But once I found out that like, they're paying their workers fairly and they're doing all these other things, they get really great health benefits. Like, all of that was going on, and they I was like, I have to shop here now. Like, there's no reason for me not to, and also like it's just better for the local community as well as just about everybody else. Right? And if we weren't so obsessed with trying to get extremely high short-term profits, then we wouldn't have this situation where the CEOs, C-suite, etc., are making like 1,000 times what anybody else in the company is. I was talking with somebody earlier, and he was like, no, you don't understand. Like, there are societies, even today, most of them in the world have policies where like they cap the highest salary in the company, and that's like through every possible means, stock options, bonuses, like everything. The absolute highest that you can make is something like 10 times the absolute lowest person in the entire company. And like that's when you talk, it is fair, right? When you talk about in terms of like hourly wage or full-time equivalent. Right? Either way. It's 10 times. 10. Like, that's it. You can't make more than that. And again, that's the bottommost person on the ladder. So is your janitor making the equivalent of full-time equivalent of like 25,000? Okay, then your CEO's capped at 250. Or the absolute maximum anybody in the entire company can make is 250,000. regardless of what source that money comes in from. And again, they're just so much more into like investing in their workforce. And there are some companies that are doing it now, even in the US, where they're, I forget what company it was. There was the CEO in like Portland. I'm sure it was Portland, Oregon, quite frankly. His minimum wage was $70,000 a year. Like, that's the minimum wage in his company, is $70,000 a year. And it ended up that his workers were purchasing houses and keeping the local economy going, and he's just like, told you. This is how we should be pretty much everybody operating. Like, you know, rising tides raise all ships. And guess which ones they're gonna raise up the fastest? It's the little sunfish, you know, the little sailboats. Those are the ones that move quite quickly. Yeah, it's just all greed. Like, I was working for an insurance company at some point, and those CEOs are making, not all of them, but you know, a number of them are making $200 million a year. Like, that's just not appropriate. Like, what are you doing? You could make $1 million a year, and you could take that other $200 million and like invest in the rest of your workforce. Again, $70,000 a year for every single person on staff probably wouldn't even be a drop in the bucket for most of these companies. You could have reinvested in the company itself. All right, maybe not like a better place or a better, you know, set of maybe not like a better place or a better set of furniture or something, but like, you know, invest in the company itself such that you're making everything better, again, for everyone. You're an insurance company. Why do your people still have to pay for health insurance? Like, why does anyone on your staff have to pay for health insurance if you're in an insurance company? Like, your copay should be $0. So, I'm going to highly recommend a book. And Georgia, you're in the UK, so you have this available now. This is Alien Clay by Adrian Tchaikovsky. It is science fiction, so like if you're into science fiction, it's a real easy read. If you're not into science fiction, it might be a little harder, but it's not that big considering his other books. Yeah, no, it's about the same maybe. His books about space spiders. Oh, that's a cool one. And actually, Children of Ruin might be a different species, but I haven't read that one yet. His book Children of Time was literally about space spiders. It's really cool. Yep. But that one is particularly relevant for right now. I am trying to get as many people as possible to read it. I don't care how. In order to understand that this is the organization that it's about organization. Like, it's about finding out the ways that things orient themselves and each other. And it's it's a pretty heavy-handed allegory, but it is definitely worth it. All right. Oh my god, and then this guy. think this is it. No. Yeah, there we go. Mabel Takes is a Canadian. He is most definitely a socialist. Lowercase s. And like, yeah, unabashedly, like, this is the way things should be run because objectively, people who are doing it now are making it work and it's doing it better. And like, a lot of people are doing it on the small scale in the United States. And now it's just a matter of like getting people to organize and scale it up and all sorts of stuff. So I'm I'm probably going to be leaning into this a bit over the next 4 years, so apologies everybody if you don't really like it, but it's life now. And who knows? When we come back to the United States in a couple of years, I have been thinking of taking an actual serious run at politics. So wild, because I hate public speaking and I hate cameras, but you know what? We friggin' need something done. So anyway, ads are about to start. I'll be back in 3 minutes. Thank you so much. Thank you, Georgia. Have a good night. And everybody else, I'll be back in 3. I mean, realistically, right? We. Thank you. It just beeped at me, so I mean, that means I got time, but at the same time, that's just, you know, we don't have to put up with that. No worries. What was the other one that we found? Right, that's just... the easy one. Over... yeah. I think I would prefer not to have that one, so let's make 2 cosine squared alpha minus 1 as our cosine of 2 alpha on the bottom. So then, that's going to make this equal 2 sine is t over the square root thing times cosine is 1 over square root thing over 2 cosine squared is times 1 over square root thing parentheses squared minus 1. Alternatively, this is going to be t squared plus 1 multiplied by everything. Yeah, leave it like that. So this is going to be 2t over 2 minus square root thing. T squared plus 1. All right, I don't know how helpful any of this is, but nonetheless. This is the tangent of theta. Okay, if we do this, then this is also going to be t, but it's not in the same position. I mean... it's not going to be in the same position. Right. So we have to back that off. So 2t compared with 2 minus root t squared plus 1. That's really gross. I don't like that. Yeah, Femvox, I'm not seeing a good way to work at this. I mean, that's just me. I mean, it's my problem, right? I gotta figure out how this all works. Don't if you have any ideas, please. Otherwise, I guess I could watch, in theory, that YouTube video on Weierstrass substitution.
Greetings, fellow.
Black t-shirt math professor. Oh, okay. That's kind of nice, actually. Okay. Okay, interesting. I think I get it, and none of this matters. So let's just go through and delete all this right here. Whoops. No, not that one. We want that one. No, not 22. Oh, you jerks. There we go. Okay. I think I get it now. So in doing the Weierstrass solution or substitution, what we're going to do is we're going to say let t equal tangent of theta over 2. Then, taking the derivative, this is going to be dt equals, this is secant squared of theta over 2, which is d theta. And also, we're going to take a chain rule, so that's a half. Okay. Then, dt can also be written as 1/2 times 1 plus tangent squared of theta over 2. Now, why on earth would we do that? Well, that's because the original stuff was in terms of tangent. So if we turn it in terms of tangent, now tangent squared of theta over 2 is just t squared. So dt is equal to 1/2 plus 1/2 t squared. And then d theta d theta equals, right. entirely what we're looking for here. So then dt over 1/2 can now become 2 up top. 1 plus t squared is equal to d theta. Lots of experience, but thank you. Right, so this is going to substitute in, this is theta equals 0 to 2 pi. D theta is going to be 2 dt over 1 plus t squared over. And then we can't do anything with that just yet. This is going to be the square root of 2 minus. Now we need something for cosine that's in terms of t. Right, we're not allowed to put in t's and thetas in the same integrand. So, to be fair, I did just watch the video on how to solve this. It's just that it was like different stuff. I just skimmed through the bottom and found the relevant section. Okay, then what we want is what is sine of x cosine of x. In this case, just cosine of x. What is cosine of x based on this? We need to get it really in terms of the other stuff. Right. Okay, so we can draw the picture here. That picture I erased. It's fine. Okay, so Pythagorean theorem, we end up with a t and a 1 for the tangent of theta over 2. All right, so it's theta over 2. And that's going to get us t over 1, so t1. And the hypotenuse is t squared plus 1, square root of t squared plus 1. Then we're going to find the sine and cosine for this. Again, sine theta over 2, not theta, is t over square root t squared plus 1. And then cosine of theta over 2 is 1 over square root t squared plus 1. We need to take this and try to find the cosine of theta, which is double the angle, which is half theta. So we take this and we plug that into our double angle theorem, which let's just use the cosine. So this is 2 cosine squared of theta over 2 plus 1 is, did I do minus 1 earlier? I might have. 1 over square root t squared plus 1 squared plus 1 is 2, might as well just do 2 over t squared plus 1 plus t squared plus 1 over t squared plus 1. Two plus t squared plus 1 over t squared plus 1, which is t squared plus 3 over t squared plus 1, is cosine of theta. So if we take that and go way back to the beginning, this one here is going to be t squared plus 3 over t squared plus 1. We can multiply both top and bottom by t squared plus 1. Okay, this is still in terms of theta, so forgive me, we'll come back to that. This is going to be 2 dt over root 2 times t squared plus 1 minus, t squared minus 3. What the hell? Okay, so we may be trying to look for something that's going to make this actually better instead of something that's really gross. Oh, it's minus 1. Yep. See, now this wouldn't happen. Minus 1, minus 1, minus 1. This is negative and negative. Okay. A little weird, but this will work. This is going to be negative parentheses t squared minus 1. Okay, so then we plug that back in. Okay, then that negative is going to mix with the negative on the outside, make it positive. We're going to multiply by t squared plus 1 everywhere. It still gets rid of that stuff, makes that stuff what you see. And then this is going to be a plus t squared minus 1. But now this is still squared 2. So, question there. Was that supposed to get rid of stuff? Sort of. Okay. So the example they had was nicer. This one's not very nice, but it'll still work, in theory. It's going to be theta goes from 0 to 2 pi. It's going to be 2 dt divided by. Here, this is going to be 1 plus root 2 times t squared plus negative 1 plus root 2 just as a number. Yep. Alright, Femvox. Here you go. This is the absolutely disgusting thing that you're going to get. This 2 can come outside. And then this all this could be 2 over 1 plus root 2 dt over t squared plus root 2 minus 1 over root 2 plus 1 and this now becomes nasty. This now becomes theta goes from 0 to 2 pi 2 over 1 plus root 2 times the inverse tangent of t over the square root of root 2 minus 1 over root 2 plus 1. Evaluated where t, nope, theta. Theta goes from 0 to 2 pi. Thank you so much, Georgia. That didn't set off with oh, right. Yeah, okay. It has to be picky. I think that's one of like the quick things to set up on stream elements. Inverse tangent of t is the tangent of theta over 2 over all that. Take it as theta goes from 0 to 2 pi. Fembox. Was this just 0? Because I'm okay with it. No, the tangent parts are going to be 0. Inverse tangent of 0 is going to also be 0, though. Right, because at 0 and pi, which is theta over 2 for 0 and 2 pi, we end up with a slope of 0. And then our inverse tangent is going to say only come from the positive one. So that's going to end up being 0. So, yeah, I think both of them come back from 0. That is slightly annoying. Yeah, sometimes math go brr. Alright, anyway. Hang on. Let's try this from Desmos. That one. 0 to 2 pi. You know what? I don't want that. I want just the function. So what is 1 over square root 2 plus cosine x? It's cute. Is it plus or minus? It's minus. Minus. Doesn't matter. Same thing. So for this, I could not possibly get a 0 for the integral. The integral, for anyone who doesn't know, is looking at what is the area under the curve. So here we're looking between 0 and 6.28, or 2 pi. And we're trying to find what is the area underneath that curve to the x-axis. So like it makes a shape that looks like this. And then we want to know what the area is of all of that. You know, like if you made it out of wood, right? What would be, how much wood would you actually be using? So this is a positive number, right? It's got to be a real and a nice kind of number. So I must be misinterpreting something. We do see 1 plus the square root of 2 in there, right? That's each of the peaks is 2.414. That's 1 more than the square root of 2. Right, 1 over square root of 2 minus cosine of theta. Yeah, it's the right function. It's kind of fun. So we go like that. Come down here, we paste it, and we do this as a plus instead. Yep. Okay, it's just offset, which also makes sense. Didn't change the overall value of anything necessarily, just where it reaches those particular values. We're going to have to go through all of that all over again. Yay! So I think what we want to have happen is that it gets multiplied by a negative square root of 2 somewhere. Like, you can't just let that happen, right? These values are always going to be slightly... So I want this to be like negative square root of 2 times that end result. So then what needs to happen to t to make that happen? Yeah. Yeah, never mind. I apparently ran out of battery or something. Shocking, really. If that happens again, we're probably just going to have to cut it here. Actually, while I've got you. Anybody who doesn't know this, it is tradition on this channel to read from John Gould's Maine Lingo, a wicked good guide to Yankee vernacular. I grew up in New Hampshire in the United States, and we had neighbors to the north who were from Maine, and further inside of Maine, there is a little area that kind of juts up the coast. If you go pretty much direct northeast from Boston, you end up hitting this area of Maine that comes out further before it goes back up. Anybody who's played Fallout 4, the one set in Boston, if you played the DLC called Far Harbor or Fa Hava, that is based on the actual physical location in the real world called Bar Harbor or Ba Hava. They have a very particular storytelling and accent, storytelling style and accent, which was preserved by two guys named Robert Bryan and Marshall Dodge. And the two of them decided to go, they were roommates in Yale. They decided to go up to Bar Harbor and, like, I mean, first of all, figure out that, like, their friend from one of their classes was not just making this up, that, in fact, this is a thing. So we will jump over to... Why not, right? Let's jump over to G. Haven't done one in a long time. Yeah. All right, we'll do 2. Um, so, G-A-N-G-I-N-G. Pronounced Ganjing or Ganging. Older and complete dictionaries have this word, but it survives in Maine with no great relationship to their definitions. In earlier times, it was that portion of a fishing line to which the hook was attached, the act of attaching such a hook, and a protective winding for the line. Today in Maine, it means a twine from which a fishing line is made, and one buys ganging just as one buys snoodin' by the hank. Ganging makes a cod line in one size, and in smaller cunner size, it's great for kite strings. A Christmas package may be wrapped with for mailing with ganging. The final G of ganging is always carefully pronounced. See sealing. Even though ganging is often misspelled, as seldom as Mainers write it, as G-A-N-G-I-O-N and G-A-N-G-E-O-N. Gangin. And also garage. G-A-R-A-G-E. Oops. When automobiles began to appear, Mainers reserved the garage for the mechanics' shops, where repairs were made. Cars were parked in the barn. In those days, garage was pronounced garage, G-A-R-R-R-I-D-G-E, to rhyme with carriage. In the early 1920s, the ladies and girls affected with a new hairdo, which was inelegantly dubbed the cootie garage. Puffs of hair over each ear suggested a stable-in place for the troublesome cooties, or lice, of the trenches from World War I. Radio was blossoming, and Maine speech began to be nationalized by it. The fad of cootie garages thus taught Maine people to say garage. There we go. Hey, All right, let's maybe come back to that later. Right now, let me just double check this one last time. Or did I close it? Yeah, I closed it. Right. So we were trying to do an algebraic method for arctan of 1 plus arctan of 2 plus arctan of 3. So the idea here was that we were going to take each of those angles denoted by our arctangents and add them up. We want to know some way that these things can be added up. So, like, if is there a nice thing that we can do? Somehow I don't think so. I mean, if we do sum of angles, Right. So I think this is going to be gross, but it'll work. So apologies, first of all, for the quality of this microphone, because this microphone is terrible. Walking Stick Library, good evening and welcome. So sorry that you're dealing with the heat right now. The only real heat that I have to worry about at the moment is from these computers, because they're pretty warm. But outside, yeah, outside's pretty lovely. We're getting somewhere around 65 degrees overnight, maybe a little bit lower. And then mostly during the day it doesn't get above 70, 75. So, anybody want to come to the UK? It's pretty nice. Okay. This will have to temporarily suffice because, like I said, I'm trying to get an actual microphone that I can like put a boom on here or something, but you know, I do have a nice little shop up the street, so I may have to see what they have on order. And if not, gonna have to wince and pull out the wallet. Triple digit heat index, yeah. It's pretty awful. Do be careful, everybody. Make sure you stay hydrated. Alright, so I think the way that we're gonna have to do this is to try to figure out what that's a plus. Figure out what we're gonna get if we add the angles on the inside and then like do that with these things. It's really kind of gross. We'll make it work. Because that's what this is, right? Boo. Yeah, of course. Tangent sum of angles. Tangent alpha plus tangent beta over 1 minus product. Okay, so for each of these, we can do this kind of one at a time here. Again, we figured out a little bit earlier just how to find the solution to this by going through and saying, all right, the approximate size of these things has to then add up to, and then we said it has to be greater than pi over 2, so it's somewhere in quadrant 2, and then it had somewhere in quadrant 2, and then it had to be less than 3 pi over 2, because that's the size of 3 right angles, and these are not right angles. So that eliminated all of the answers but 2, I think, right? Like exactly pi over 2, or then pi. So all the way over. And since our smallest angle, the arctan of 1, is 45 degrees, then that told us that, well, if we're going to add up 3 of them, it's got to be at least 135. So it has to be more than 3 pi over 4. And so naturally that leaves only pi as our answer. It's the only thing that was left. Alright, so then we look at this and we say we've got to add up the arctan of each of these things. So we've got the right? So the arctan of 1 is going to be this particular triangle here. Arctan of 2 is going to be this one, and arctan of 3 is going to be that one. So we want the sum of those 3 angles based on the trig formula right there. We're going to have to do this 2 at a time, so let's just add the first 2 together. It's going to be the tangent of, I don't know, we'll call this one alpha and this one beta and this one gamma. So alpha plus beta is going to be, the tangent of alpha is 1. No. Tangent of alpha plus tangent beta. Oi. You know what, let's just, we already have the formula written up top, so we're not going to worry about it. Alright, this is 1 plus tangent of beta was 2 over 1 minus 1 times 2. So this is going to be 3 divided by, and then this is 1 minus 2, so that's negative 1. So negative 3. So then the tangent of alpha plus beta plus gamma is going to be equal to the tangent of alpha plus beta, which is negative 3, plus the tangent of beta, tangent of gamma is 3. Oh. That's correct, actually. Over 1 minus negative 3 times 3. It's going to be positive 9 plus 1 is going to be positive 10. So that's 0 over 10 is 0. But that's true because tangent of either 0 or pi are both 0. So that's going to tell us in this case, right, the tangent of the sum of the angles is going to be 0. Out of all these right here, only one of them does. Right? It's pi. Right, so this says that alpha plus beta plus gamma must be equal to some multiple of pi. Right, if our tangent is 0, then either we've got to get 0 or pi or 2 pi or 3 pi or 4 pi or 5 pi or negative pi, negative 2 pi, negative 3 pi, etc. So one of those. And yeah, none of these other numbers are going to be equivalent to a full multiple of pi. Just pi itself. Well, it's pretty obvious when you say it like that, I guess. No. Alright, as promised. Woo! I was wearing a flat cap all day, so like my hair's all messed up. And when I had my headphones on, it was fine. You wouldn't have noticed. Alright. A full 50% of questions on the GRE math subject tests involve calculus, which includes differential equations. We'll review single variable calculus in this chapter, multivariable calculus in chapter 3, and differential equations in chapter 4. Alright, so the first thing that they talk about is sequences, which is interesting because, like, this is the last topic in my pre-calculus class, and they're doing it here as calculus. Specifically, right, they're looking at taking a string of numbers, a list of numbers, stringing them together, and then this is just what is generically called a sequence. It doesn't have to have a pattern. It doesn't have to have any nice sort of like stuff to figure out, but it's nice when it does. When it's predictable, when we can figure out relationships that it has with other stuff, that's more interesting. If you just came up with a sequence of random numbers, which is perfectly valid, it's not particularly interesting mathematically. Like, it might have some sort of significance psychologically. Cesar. Yeah, sure. If you feel like it. So this may be infinite or it might be finite in length. If it is finite in length, then generically you could also say, like, there could be an infinite list that comes after it of all zeros or something like that, but it won't necessarily be literally all zeros because that would be different than being blank. There's a bunch of options. Alright, so generically speaking, we're going to say that all these values are usually real numbers. So they do not have any complex non-real component to them. They're just going to be all real numbers. If anybody doesn't quite know what real numbers are, right, we have the natural numbers, the numbers you started counting with. So 1, 2, 3, etc. We have the integers, which are whole numbers. We have the rational numbers, where we do not let b equal 0, but a and b have to be integers. We have the algebraic numbers. Algebraic numbers are just going to be, basically this is where we start very generically describing the kinds of numbers that you can get. Algebraic numbers have to be solutions to polynomials with rational coefficients. The rational numbers are the ones above them. Rational numbers have to be the ratio, rational, of two integers. And nope, not natural. Ugh. It's better at least. Right, so algebraic numbers have to be solutions to polynomials with rational coefficients. And then we get transcendental reals. Which are going to be like everything else. Right? This is just no other pattern like the ones that are above it. This can be something like pi. This can be something like e. This can be, algebraic can be like the square root of 2. 1 minus 5 times the square root of 3, that sort of stuff. The fifth root of 7. There's all sorts of stuff that you could do with algebraic. Transcendental also includes stuff like 0.10100100001 and that kind of stuff. So those kinds of numbers we can't actually do anything with the right. This pattern doesn't exist in the other stuff above it. So if we tried to make that the ratio of two really, really, really big numbers, it just won't work. Maybe. I mean, like, I don't have a real, like, favorite book that's related to politics in anywhere near the same vein as probably what you mean. But I would say you would want to at least familiarize yourself with Plato's Republic and why we probably don't want a pure republic, because quite frankly I don't think social castes are a good thing. See, the other thing is that, like, a lot of books written by politicians aren't written by politicians. They're written by ghostwriters who do all that hard work for them. Now, some of them do write it, especially, like, you know, people with law degrees are used to writing a lot, so oftentimes they can figure stuff out. But and if they're smart, then they've got a good publicist and a good editor. So the editor's going to go through and be like, this doesn't work. put this over there, put that over there, you know. A strict chronological telling of your story may not be the best in your best interest. That kind of thing. But yeah, Plato's Republic was a good read way back when I read it in Philosophy 101. And again, definitely why we do not want to have a pure republic. And why the United States was set up as a democratic republic. Or approximately. Representative democracy was one of those, like, good ideas that at the moment is having a bit of a problem. We've got some hiccups. But a lot of other places are at least decently doing a reasonable job. Right. So this is the reals as a whole. Right, this is the real number system. This is what we're going for with the sequences, that all these end up being real numbers of some kind or another. They don't have to be one particular type or another. They just have to be all real. I want this to say for all a sub I, as I starts going to infinity, so a sequence will be convergent when convergent to a limit L when for all what is called epsilon greater than 0, there exists some n such that the difference and the absolute the absolute value of the difference between a sub I, a sub n, sorry, a sub n and the limit value will be less than epsilon. For all I. For all I greater than that particular n. So this is like the crux of pretty much all of calculus. It's not particularly easy if you're just looking at it. So you really have to like try and understand how all of this works. It's a little weird. Visually speaking, right? We can do this visually. If I have a sequence of numbers, and they don't have to necessarily be monotonically increasing, as in always going up, right? They can kind of jiggle around and do all sorts of stuff. But the important thing is that if we have some sort of limit value, L, then what I can do yeah, thank you. Nintendo Pharmacon, welcome back. Good to see you again. So what we've got here is that the distance, which we can call epsilon, will at some point have a value such that, right, for every single point, for every single a sub I, for every single other value that we have in the sequence that is beyond this line, so not at this line, but beyond this line, every single other one is going to be above that particular epsilon. Did I just skip? Yeah, I totally skipped an ad break. Sorry, everybody. I know that was like 10 minutes ago, apparently. Woo! Okay. So, as our index, the little I there, as the index gets bigger and bigger and bigger, so as we go further and further along inside of the sequence, this particular sequence will be convergent to this limit L, the hard line, if for every possible number that we ever pick that we call epsilon, we're able to find some location where everywhere beyond this point, all of the rest of the sequence points are going to be closer to the hard line than our epsilon line. So, an example. F of x equals 1 over x. Super simple, super easy, right? Hardly ever have to think about it. We know that this sequence converges to 0 because as x goes to infinity, this is a function, not a sequence, but it's the same kind of deal. As x goes to infinity, our f of x is going to 0. Okay, so pick any value that you want for epsilon, a tiny, tiny amount. Right, so let's let 1/millionth. Right, let epsilon be 1/1,000,000th. when x is greater than 1 million. This one's super easy. When x is greater than 1 million, f of x will always be less than 1 over 1 million. Right? Let epsilon be 1 over 10 to the 5,000th. Okay? Again, when x is greater than 10 to the 5,000th, f of x will be less than 1 over 10 to the 5,000th. So in this case, no matter what we do, we have this relationship that exists, right? For all epsilon greater than 0, we have that when x is greater than when x is greater than 1 over epsilon, f of x is less than epsilon. So since we can come up with this particular relationship, we can let n be equal to 1 over epsilon, and then it always holds. So whenever x is greater than this particular n value, which is 1 over epsilon, then we're always going to get f of x less than that same epsilon. So therefore, right, f of x equals 1 over x converges to 0. So we didn't really do that last step in order to show that, not only does it converge, but it converges to 0. But generally speaking, if you're doing this, right, most people get the numbers that are going on here. And again, I think we did say up here, right? Yeah. As x is going to infinity, f of x is going to 0. So this is going some of the way to proving that this is actually the case. This is not a proof. At least not a real good formal one. Some teachers might be perfectly happy to let you just kind of reason your way through stuff. For me, it kind of depends. And then if no such limit exists, f of x, no, a sub I diverges. So let's say every 500th term ends up being equal to anything, 1, right? Every 500th term is always 1. Well, that means that we can never get lower than an epsilon of 1, even if the rest of the sequence is converging to a specific location. So, in that case, a sub I would diverge because it never reaches a single limit value that's going to work for all epsilon and for all n. if sequences diverge to infinity, sometimes we say that they will diverge to infinity and treat it as though it were approaching a particular limit value. So it's a little weird that we talk so much about infinity, but that's kind of where mathematics goes. Nope. Nope, don't do that. Right, often we'll say that we're diverging to infinity or diverging to negative infinity if the sequences diverge and approach an infinite value. So it kind of depends on, again, who you're talking to. So oftentimes this will be something like as x approaches infinity. No. A sub I. No. As I approaches infinity, a sub I approaches infinity. So, something like that. Oftentimes. I brought up a word earlier that was right, monotonic or monotonically increasing or decreasing. Will be for all I greater than some particular n value again. X. I keep doing X because it's in this book. So a sub I will be greater than or equal to all further a sub I plus 1s. So for every single I value that we pick, the next one up will be increasing. Still increasing again, forever. Or it can be equal, so we can call it monotonic if it stays the same, monotonic. whether that is the actual same value or if it's just steadily increasing. Even if it's not linear, it can end up being like logarithmic or not quite what I put back here, because again, this is kind of jumping around over in this section. But if this was just all either increasing or the same, then that would be monotonically increasing. If you look at a logarithmic function, right, that is going to be monotonically increasing. For every value that we pick, if we move to the next value over, we're still increasing. All convergent sequences have some m such that the absolute value of a sub I, right, just the value of this thing will always be less than that particular m. In theory, it could also be less than or equal to as well. So again, pick a number, and then every value in the sequence, or every value in the sequence beyond a certain value, never goes, well, no. Let's just keep it as a whole. It will be bounded if every a sub I has a distance from 0 that is less than that particular m value, or equal to. Every monotonic and bounded sequence will be convergent. Sequences and their limits may behave as with their linear, or as with linear operators. So there's a way to describe this, right? So linear operators allow for a few properties. right? These are the big ones. So a linear operator of a plus or minus b is going to be equivalent to the linear operator on a plus or minus the linear operator on b. So this is effectively it's not distribution. Don't say distribution. Right, so linear operators end up affecting the inside, like the sums or differences of the inside of their parentheses. The same whether they are combined, the linear operator of a plus or minus b, or separate. Linear operator of a, linear of operator of b, take its sum or difference. Same behavior. Also, if k is a constant, then k times a affected by the linear operator is equivalent to taking the constant out and multiplying it by the linear operator of a. One of the more fun things that we get into eventually is what happens if k is a function, but it's only a function on stuff that doesn't affect a at all. In which case, you treat it like a constant. But that line is very thin and very treacherous, so maybe don't play with it too much. So for this means that, right, we could do the same with sequences. So if the limit as I goes to infinity of a sub I is equal to capital A, and the limit as I goes to infinity of b sub I is equal to capital B, then limit as I goes to infinity of a sub I plus or minus b sub I. So these are sequences. Yeah, okay. That limit is going to go to, or I suppose that limit is equal to, capital A plus or minus capital B. Also, limit as I goes to infinity of k times a sub I is going to be equal to k times capital A. Alright, and then we get extra bonuses which are not linear operators, but the limit as a goes to infinity of a sub I times b sub I. So individually, we take that list and we match up all of the a's with all the b's, and then we take their products of your a times your b in each of those individual positions. It is also true that if we keep going on and on and on forever, that as we get further and further along, we're going to notice that the product of the individual terms a times b are going to get closer and closer to capital A times capital B. So the product of their individual limits. Close enough. Right, that also means that division works too. Provided that b is not 0. And in fact, no b sub I is going to be equal to 0 either. Because then we won't be able to take that ratio. In theory, you could also say that, like, oh, just one of them is going to be 0, but that's alright. Hey, Dr. Gold, how's it going? My headphones died, so I'm doing the crappy thing. Hey, Shanktrix, how's it going? Yeah, it's alright. It's not like it, you know, died. It's just that I had to plug it in. And then it kept dying while it was plugged in. So I said, you know what, I'm not going to mess around with the battery. I'll let it recharge. Let's see, any others? I mean, realistically, I need, you know, a real microphone. But we're slowly getting there. I don't really know where they're going with these last couple of bits here. But they're like, oh yeah, well, if k is a positive constant, then 1 over I to the k is equal to 0. And like, I guess. But we're not using I all that much in sequences. I mean, like, the thing. Anyway. Blue Yeti. Yeah, I've heard good things about Blue Yeti. I've also heard bad things about Blue Yeti, but maybe it's just that those people didn't like it because, you know, it's cheap or whatever, or it doesn't sound as good, which, okay. I could probably deal with it. But I'm also like a Logitech shill, so who knows. I don't want Logitech for that. Hang on. No. What was I doing? Whatever. Is that a thing? No. Okay. Just checking. Yeah, I got I put a beacon mic on the crowdfunding thing, but not the point. Oh, yeah. The squeeze theorem. This is also another thing that was included so that you just make sure that you understand how sequences work. So if we end up with sequence A sub I, B sub I, and C sub I, such that for all I greater than, again, some particular values where we start looking. It doesn't matter what it is. So wherever you want, start looking here, and for every value beyond this, any particular A value is less than or equal to any particular B value is less than or equal to any particular C value. And the limit of, as I goes to infinity, of A sub I is the same as the limit as I goes to infinity of C sub I. Then this means that now we've got two sequences that are drawing closer and closer and closer to the same limit value. Then this means that the limit as I goes to infinity of B sub I must also equals L limit value. Limit as I goes to infinity of B sub I must also be L. So again, you've got a sequence that's up here, you got a sequence that's down here, and they're moving toward the same value forever. And there's some other sequence that is between them forever. And that means that that between sequence must also converge to the same limit value as the other two. I think typically the favorite to use for that one is if A sub I is equal to negative absolute value of x, not x, negative absolute value of I, C sub I is equal to the absolute value of I, and then B sub I is equal to I times sine of I. Alright, your sine value of I, no matter what I is always going to be between -1 and +1. And then the I value is just the I value, whatever it is. So you end up with now values that are showing us that that doesn't really work. Yeah, we need a continuous function for that one. Give me a sec. Better one. A sub I is equal to -1 over I. C sub I is equal to +1 over I. And then B sub I is equal to I mean, we could do that again, but 1 over 2 I squared sine of I. Right? We could play around with this all we want. No. No. The sign can't be there. Damn it. There. There we go. Alright. B sub I is equal to the sine of I over 2i squared. So in this particular case, again, sine of I has to be between -1 and +1. And then our I keeps getting bigger. So in the denominator, i's get bigger. Therefore, the fraction gets smaller. And if we make it now 1 over I squared is going to get bigger faster in the denominator, which means that the whole fraction will get smaller faster. And then the 2 in the denominator is also going to halve it, so it's going to make it even smaller. So since 1 over I is going to go like this, and -1 over I is going to go like this, both of these values are, as I gets really, really, really big, 1 over that thing is going to get really, really, really small. So those two things are both converging to 0. And B sub I is going to remain between them for all I values. Greater than 1, probably. Possibly greater than 0. Seems like it. Again, I is going to be an integer, so we can't do like 0.2 or anything like that. So because of that, we're seeing that B sub I has to also converge to 0, because it will always be between A sub I and C sub I, and those both go to 0. So therefore, B sub I must also converge to 0. And I'm going to call this the correspondence theorem. If the limit as x goes to infinity of f of x equals L, then, and this actually goes both ways, so we could do this as if and only if. Okay, so if the limit as x goes to infinity of f of x is equal to L, nope, not if. The limit as x approaches infinity of f of x is L if and only if. So this logic goes both ways. Not lif. That's a Douglas Adams book. If and only if the limit as I goes to infinity of a sub I is equal to L. Okay, there was one thing I forgot. It needs to be true that for all x equals I, f of x equals a sub I. Then this other thing will be true. So I'm going to call this the correspondence theorem. If you have a function that corresponds to every single sequence value, so they have exactly the same value at all of those indexes, then it turns out that they're going to have the same limit as each other as well. That's not really surprising. It's just kind of, something that would have to be formalized ahead of time. Okay. I'm going to stop this nonsense, and we're going to head on over. Oh, we're going to go see Dr. Gold. Oh, wait. Hello? Oh, no. That's, that would be Russian. So I suspect that person is not doing math in English. Let's go see. Oh, pen stream is ending. Let's go see. Hey. Good evening, Penn Center. Good evening, PhD Lingo. How you all doing? Unfortunately, we're just heading out as well. I'm going to go over to Solu9, who is a friend of ours from Psyches. Right now he's doing some Canadian cuisine, making poutine, beaver tails, donair, and bagels. So we're going to go make ourselves hungry. I will be back on Wednesday for more math stuff, Friday for more game stuff, and whenever else I feel like it. So I hope you all have a good night, and we'll catch you next time. Sorry to get you all out of here as soon as you came in. Oh, man. But thanks, everybody, for coming. My name is Obi-Wan Pez. This is Ensign Plix Pachinko, and I'm going to fix my audio before next time, so see you guys next time. Charge the battery,